Hey guys, today you're going to learn about log functions.
Can't read what this says. Say have fun.
Have fun.
As a little hint to who that person was, he is in the social studies department. He teaches psychology this year. He lives in the city, and I don't think many of you have had him, so that's not helpful. But that's okay. Anyway, back to the math. We are talking about logs. We just spent a lot of time talking about exponential functions. So let's talk about log functions. Here's our first example, which does involve an exponential still. It says find the inverse of f of x equals 3 to the x. There's a reason why we're doing this, to introduce logs. Maybe you already know. But yeah, let's find the inverse. So don't forget, anytime that we're solving for inverses, we always switch the x and y values. So I'm going to have you guys try this one on your own. If you're not exactly sure how to graph this, maybe you find x and y values for this function, f of x, and then switch them and then graph. Okay, see what you guys come up with. All right, go ahead, put me on pause. So hopefully you got a graph that looks something like this. Notice here that, there's really two ways we could figure out the inverse of f of x equals 3 to the x. We could switch x and y and then solve for y. So actually the inverse of 3 to the x is log base 3 of x. So in other words, the inverse of the exponential is the log with the same base. Wow. Or I could have also figured it out by plotting some x and y values for f of x, switching them, so switching the x and y, and then plotting them, and those also give me the values that would satisfy this inverse equation here. Something that I want us to note is that this graph does have a vertical asymptote, which is actually different than the asymptote in an exponential, whereas that one had a horizontal asymptote. So to just state some characteristics of this graph, So we have a vertical asymptote at x equals 0. The domain is 0 to infinity. The range is negative infinity to infinity. The y-intercept is none, and the x-intercept is 1, 0. What I'd like you to do right now is I want you to page back to the 6.1 notes where we talked about the characteristics of an exponential graph. Go ahead, do that. Here's my sound effects, paging back. Ooh, good sound effects, T. Okay. You should notice something very special about the characteristics of the graph of an exponential in relationship to the characteristics of the graph of a log. That's mind-boggling. Okay, so general definition for a log. Okay, notice that we have some restrictions here for x is greater than 0 and a is greater than 0, and also a is not equal to 1. So a could potentially be, a positive decimal value. Y equals log base a of x if and only if x equals a to the y. In other words, these have an inverse relationship. Okay. Now, using this definition above here, this is like my favorite color. Not really, actually, I changed my mind. But anyway, using this definition, I want you guys to evaluate the following. If f of x equals log base 4 of x, what does f of x equal when x is 16? And so on. I want you guys to try these on your own and have you guys think of this. Okay, so go ahead, put me on pause. So let's see what we did here. Now, all of this is related to this definition here, okay? This conversion from log form to exponential form is probably the most important skill in this unit, to convert from one form to another. It truly is a prerequisite skill for all the other skills that we're going to learn in this unit, so if you don't understand this, make sure you do, okay? But this notation here is asking, basically, log form says 4 to what power is 16, right? If I change this log form to exponential form, which I did from here to here, I can see easily that y is 2. Okay? That's what I did for the other one. So 2 to what power is 64? 6. 5 to what power is 1? 0. 3 to what power is 1 over 81? That's negative 4. I could have also written that as like 81 to the negative first power. Maybe that would have helped. I don't know. Okay, let's try some more. It says this time write the log equation as an exponential equation and then solve for y. So 2 parts here. Convert it to an exponential, then solve. Go ahead and put me on pause. So let's check our answers here. Hopefully you're able to convert these to exponentials. 2 to the y is 16, so y is 4. Here, 2 to the y is 1/2, so that's y equals negative 1. You could have also used some log properties here, that, and actually we're going to review this shortly, but our log properties say that if I have a quotient of a log, that I can actually split those up as a difference of the logs with the same base. Once I do that, I know that I have log base 2 of 1, which is 0, and log base 2 of 2 is 1, so I still get negative 1. But the directions did ask you to convert to an exponential, so what's in red is probably the preferred method here. Here, so I convert to an exponential, I get y to the 5th equals 17. To solve for y, I take the 5th root of both sides, so I get y is the 5th root of 17. Here are some properties of logs, just as a review. So what I'd like you guys to do is see what you can remember. Fill in the blanks here and see if you remember your properties, okay? And then we'll unpause and check. Go ahead. Log with any base of 1 is always 0. Log base a of a is 1. Log base a of a to the x is x. A to the log base a of x is x. Notice that if these didn't have matching bases, this wouldn't be true. And then this last one, it makes the most sense. Log base a of x equals log base a of y, then x equals y. Okay? Remember here, this is saying a to what power equals 1? 0. A to what power equals a would have to be 1. And then just another thing I want to remind you is that notation-wise, anytime we have log base a, like I can never have this alone. It has to be log base a of something. All right? Something to think about. Is there a log that perhaps appears more often or is more useful than other logs? Well, the answer to this question is yes. It's called the common log. It has a base of 10. And, you know, anytime that you ever see log without a base, you know, we assume that that base is 10. Now, just so you guys know, on your calculator, the common log button is the log button. So if I type in like log of 5, that's actually log base 10 of 5, but we don't write the base. Also, if you do have a newer calculator and you're wondering how can I write a log that has a different base, let me remember this. Thank you. There it is. So you're under math, first column, log base, enter, and then it allows me to have a base other than that, so maybe log base 2 of 6, I don't know. Okay, just so you guys know calculator-wise. But back to the common log. Oopsies. Sorry, sometimes this is just crazy and annoying. But yeah, back to the common log. It does have that base of 10. Need to scroll down here. See, this is just so annoying. Let's see if you guys can evaluate this, and 3 of them you're going to have to do on your calculator. Okay? So go ahead, put me on pause, and evaluate these 3 logs, common logs. So the first example, perhaps you could have figured that out without having to plug that into your calculator. That's 2. The next one, plug in your calculator, you get negative 0.398, and you get 0.699, and this one doesn't exist. Why is that? I'm going to put this in parentheses just to see. By the way, this is not log base 10 minus 4. Remember, it's log base 10 of 4. You always have to have log of a value. Why doesn't it exist? Well, go back to our restrictions on logs. Remember, x has to be greater than 0. Okay. Then, is there a log that just seems more natural? Natural. Logs, natural. I can think of a million funny jokes right here. Anyway, write the following exponential function, the natural exponential, as a log. How would we do that? Oops, not by drawing random lines. Delete the natural log. Now, how do I get rid of this guy? Well, we have something called the natural log. You guys have hopefully seen this before. the natural log is 4 when x is greater than 0. It is the same thing as log base e of x. But instead of writing log base e of x, we just write natural log of x. Now, you might be wondering, why don't we write NLX? And why is it LNX? I don't know. I didn't make it up. But it's LNX. But please, 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 if I were you, I would say natural log of x when you read this out loud. Like if I'm reading out loud natural log of 5, don't read out loud ln5. Instead, say natural log of 5. You'll sound way more educated. In fact, my teacher in high school used to make us pay 5 cents every time we said ln. I'm not that mean. But don't forget that x has to be greater than 0. That still applies. Okay? So, some properties of natural logs, they actually are the same properties as any regular log. Let's have you guys fill these in. Go ahead, put me on pause. Natural log of 1 is 0. Don't forget, anytime any base of 1 is 0. Natural log of e, well, I have log base e of e is 1. Natural log of e to the x is x. E to the natural log of x is x. And then if natural log of x equals natural log of y, then we can assume that x equals y. Again, these are all the same properties that apply to any old regular log. Let's practice rewriting, or in other words, converting. So please rewrite this log equation as an exponential. And then once you do that, please write these exponential equations as logs. Go ahead and put me on pause. Our answers here. Remember, converting from log to exponential form or from exponential form to logs is insanely important. Okay? So to rewrite these, the base of this log is e, so e to the 1 point blah 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 is 4. E to negative 0.47 blah 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 is 5/8. Down here, converting from exponential to log form, we get natural log of 0.01 blah 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 equals negative 4, and natural log of 2.1 blah blah equals 3/4. Is it faster to say blah, 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 or just say the numbers? I don't know. Okay, tune in to part 2 to finish the notes.